Hi students, morning. Welcome back to our channel Biochem Live Classes, online classes, and please like, share and subscribe our videos. So आज जो हम पढ़ने वाले हैं, that topic will be in organic chemistry. Organic. Everyone says that this is the hardest part in class 12, but I don't believe so. ऑर्गेनिक केमिस्ट्री बहुत हार्ड होता है, लेकिन ऐसा कुछ नहीं है. दिस इज़ द मोस्ट ईजीएस्ट पार्ट इन केमिस्ट्री एंड इसको हम लोग आराम से सॉल्व कर सकते हैं. ठीक है, सो लेट्स मूव ऑन. सो हम लोग का चैप्टर है Haloalkanes and Haloarenes, and we will be going by our syllabus and covering each and every topic according to the NCERT. Okay, so let's move on to our classes. First, let's see the terms haloalkane, right? So what is haloalkane? Suppose this is an alkane. I'm having propane in here. This is propane, right? Propane. Hence it is an alkane. Now I am trying to add a halogen group in this particular section. What's happening in this case? If I transform this one into this one, in this way I can see that in here I have attached a chlorine in here. Hence this is a halogen group, right? So alkane plus halogen. Now what we will do, we will just take this part in this section, right? Then halo means halogen and alkanes are the straight chain groups in organic chemistry. So both combine together to form haloalkanes, right? So this is the term haloalkane. First let's see how particular haloalkane can be formed. Then we'll go for the preparations and let's see what are haloalkanes basically. In case of, suppose I'm having a methane in here, right? What happens if I'm having a chloride radical in this section, chloride ion in this section, and this hydrogen is removed from here and chlorine enters in this section? It will give the same methane structure with the chlorine or halogen in it, right? Hence X can be Cl, Br, F. Okay, alright. I is not that much mandatory like these elements are in here. So now we are having a particular structure of chloromethane in here. This is chloromethane, right? So what will have if we combine a halogen group? If we insert a halogen group in a particular alkane, it will form structure known as haloalkane. So halo comes from the chlorine portion and alkane is due to the aliphatic chain. Okay, so this is all about how the haloalkane is named, how the haloalkane is formed in general. Okay, so write it down, this one. Then we'll move towards the naming of haloalkane and then the preparations of haloalkane. Remember, in class 10th we have studied another thing. We have studied about preparing haloalkane, right? There was a substitution reaction. A substitution reaction was there in which this was methane, and if we kept that methane under sunlight in presence of chlorine, ClCl, that means Cl2, right? What would happen? A particular chlorine would form HCl, and this section will come to this one, right? Then what will happen? It will form plus HCl. So we are having a chloromethane. In here we are having a chloromethane, right? Now how this substitution takes place? We will modify this one, okay? We'll go into a detailed structure of this one. Let's see what happens. First, due to the inductive effect and higher electronegativity, the electron in this case are pulled out in this particular section. But particularly in this substitution reaction, what can we see? There will be a homolytic fission. A homolytic fission will be there. What would happen? It would form one radical of methyl group, and in case of chlorine we will get the same kind of thing, and we will get two radicals of chlorine, right? So one chlorine will shift in this section, and we have, and another hydrogen will combine with this one, forming HCl, and in this case one chlorine which came in here will combine with this one, and hence will be forming the chloromethane. So this is how the haloalkane takes part in substitution reaction, and haloalkane is formed, right? So let's move on to the details of the chapter. Okay, so now there was another topic known as haloarenes. Why those are called haloarenes? Suppose in case of haloalkane we are having a halogen group in here, and then we are having a benzene ring containing group in here. So what would happen? These two will combine to form a particular structure like this one. This will be known as haloarene. Halogen plus aromatic group arene. So this is the portion of arene which is brought out from a particular aromatic group, and this halogen portion will be brought out by a single elemental halogen, right? So this is how the haloarene is formed. Okay, so now what we will be looking at is the classification of the haloalkanes, right? So there might be different categories of haloalkanes according to their classification, and that could be on the basis of numbers, and then numbers of halogen atom. Number 2, that could be on the basis of sp2 CX bond, that is the carbon halogen bond between them, where X may be defined as FCl, bromine or iodine, and in number 3 what we will be having that they can be of sp2CX bonds in case of the aromatic di-in compound, di-in or in or aromatic compound. Okay, so then the haloalkanes and haloarenes we will be discussing today. Okay, so these could be the classification basis: number of halogens present in the particular compound and number of CX bond or sp2 CX bond present with FCl, Br or I, and then in number sp2CX bond in case of di-in, in and aromatic compounds. Right, so let's move on to the first category. Structures that are dependent on the number of halogens. Number one is the monohalogen compounds, monohaloalkanes. Why these are known as monohaloalkanes? As they will have only one single halogen atom in the structure, right? Like this one, we can have this one. This will be a monohaloalkane structure where X could be, where X is equal to Cl, F, Br and I, right? In case of dihaloalkanes, in case of dihaloalkanes, we can have two structures, two carbons having CX and the remaining will be hydrogen, right? Then in case of trihaloalkanes, what we can have, there are three halogens present in these structures. So on the basis of number of halogen present, we can have monohaloalkane which will consist a single halogen atom, dihaloalkane which will consist two halogen atom, and trihaloalkanes which will consist three halogen atom. In case of haloarenes too, we can have that one mono, di or trihaloalkane kind of structures. Let's see how in case of haloarene the main structures work, right? So in case of haloarene we can have monohaloarenes with a single halogen structure. Then in case of dihaloarene we can have here, we know that this is para, this is ortho, this is meta position, right? We can have it either on the ortho position or even the second one in the meta position, right? And in case of trihaloarenes we can have a structure like this one, having three halogens at para, ortho and meta position in according to their group and the stability of the structure. Now we will be moving on to the first, second or third allylic hydrocarbon. So depending on the number of halogens, we have seen that they could be mono halo or mono di or tri-haloalkanes or haloarenes, right? Now we will be moving towards the next classification, that is what I have told you, sp2cx, right? In case of sp2cx bond, we can have the second thing, that is known as 1 degree or primary haloalkanes. Number 2, secondary haloalkane, and number 3, tertiary haloalkanes. This could be on the structures of allylic halides also, right? So on the basis of this one, we will be studying the haloalkanes in case of RX bond formation, right? So in case of primary haloalkane, what we will have, RC now this carbon is 1 degree carbon, and even this carbon is 1 degree carbon. When we say that this is a primary structure, when there will be a bond between two subsequent carbon, it will be known as 1 degree carbon, right? Hence this carbon is associating a particular halogen group in here. This halogen group will give it a name of primary haloalkane. Why this is known as primary haloalkane? As these two carbons, this carbon which is a 1 degree carbon in here is associating with the associated directly with the halogen group, right? Now the secondary, this was primary, now this is the secondary structure, and this, in this case, we will be having two R's, R and R dash. Okay. As this carbon, this is a 2 degree carbon now, right? This is a 2 degree carbon. Now as this carbon is associated with two other carbons like this one, then this will become 2 degree, this will become 1 degree, this will become 1 degree. And in this particular case, when it is associated with a 2 degree carbon, it will be known as 2 degree haloalkane, right? And in case of tertiary haloalkane, what we can have, that a tertiary haloalkane or 3 degree haloalkane will be having 3 R groups associated with this center carbon, and if this carbon is primary, tertiary, and the halogen is associated with this one, this carbon directly, it will be known as a tertiary haloalkane compound. Tertiary haloalkane compound. Okay. Now, in case of sp2, so all these are aliphatic kind of structure or alkyl halides in general. These are alkyl halides in general. Now we will be moving towards our next structure, that will be the allylic halides, right? So what happens is, you can write it down, write all these structures right down in your copy, and then we will go for the next category. Now if there is one allylic hydrocarbon allylic haloalkane, it will form a different kind of structure, but suppose this one CH2X, what would happen if we go for the in detail structure? It will show a structure like this one, right? It has a double bond in here, hence it could play a role. So this will be the sp2 one, right? And then in here we are having another carbon, and what would happen next one, we will get a halogen in this section. So this could be chlorine, fluorine, bromine or iodine. So if a double bond is present, suppose this is the carbon associated with the group, then this is alpha and this will be known as beta carbon, what we have studied in earlier in class 11. So what we can say that particularly we will be having a group beside this one, then this one will be the alpha carbon in this particular case. Now in case of haloarenes, it's not haloarene, allylic halide. We can have certain cyclic compounds too. Cyclic compounds. Let's see, hex diene, or not hex diene. Let's see, cyclohexene. Now, in case of cyclohexene or monocyclohexene, what we can see, it will be a structure like this one. So it is having a sp2 center in this section, right? But all these nodes 1, 2, 3 will be, and even this one, all this one will be sp3 hybridized, and this one will be sp2 hybridized in this particular case. And now let's move on to the next one, that is the benzylic halide, right? So we will be moving to our next one. Last one was allylic halide. Now we will be moving towards the benzylic halide. Let's see how benzylic halide, with the name we can associate that a benzene group will be present in here. A benzylic halide, in case of benzylic halide, a benzene group will be present. In this particular section, we can have a structure like this one. These, in this case, suppose we have taken CH2OH. So this will be known as the benzyl alcohol. But if I remove this one and associate a chlorine in this particular case, then we can have a 1 degree of benzylic halide. So this carbon will be a 1 degree carbon. So this will be known as 1 degree benzylic halide. Okay, then next we will be moving for the next one. Then we can have a 2 degree structure associated to here. Then 2 degree or secondary structure, we will be having so in this case the hydrogen will be replaced by a particular halogen in here, right? So this one will be 2 degree, as this carbon is 2 degree, this was 1 degree, and this is 2 degree carbon. As I have told you earlier that halogen is directly combined with the 2 degree carbon, it will be known as a secondary or 2 degree halide. Okay, so we will be moving for the next classification of vinylic halides and aryl halides. So we will start looking at the phenylic halide and the aryl halides, right? So why we say that it is a vinyl group? Why it is known as a vinyl group? In sp2-CX section, sp2-CX hybridization, we can have a phenylic halide. When we are having a CC group like this one, and halogen is directly associated with a carbon having a double bond or sp2 center, right? So this one, in this case, this carbon will be known as a vinyl carbon, or this group will be known as a vinyl group. When in case of, suppose this one, I have written this one, this is in your NCERT book. Now previously what we have written right here, then CH2X, this was our structure, this was previously, this was in case of the arylic halides. But in this case what we will be having, this is arylic, right? Because it is not directly, the X is not directly associated with this one, it is directly associated with this carbon. But in case of, in this case, in case of vinylic structure, what we will get, it will be directly associated with the double bond associating carbon molecule, right? So this will be known as the phenylic halide, and afterwards what we will be having is our aryl halides, right? Now let's move for aryl halide structure. What we have written earlier, that there could be a number of structures depending on the aromatic group, right? Suppose in case of aromatic groups, we are having an aryl halide, suppose this one. Lastly, in case of benzylic halide, what we have seen, this is aryl halide, so this will be directly associated with the ring, right? This is directly associated with the ring. This is a 2-degree carbon, right? But in case of what we have seen earlier, in this particular case, that we will be having a benzylic halide. In case of benzylic halide, what we have seen, that a benzene group associated with CH2, then we will get one with this one. But in this case, aryl halides we will get 2-degree sp2, right? sp2 hybridization. But in this case, this will be 1-degree sp2 CX bond. So this was the chance of classification. This is the classification portion we have discussed earlier, and for the nomenclature what we have learned from class 11, you can go for the IUPAC naming. I am not covering that nomenclature portion, I will be taking it later. And so what we have studied earlier, these are the structures of organic halides, and we will be moving on the different kinds of structures that we have to go for in this section, right? So next topic will be the nature of. Now in our last video we have seen that the classification could be according to the placement of halogen atoms, right? So in this particular video we will be talking about what would be the nature in case of a CX bond. So we know that there is sp2-CX bond in case of haloalkanes and haloarenes are present. So in this section we have seen that there's one, suppose chlorine is given, right? Then we will have particular hydrogen structure, so we are having chloromethane in this case. We often write D negative and D positive in this section. So why we write that? We will go for this one to understand what is the nature of the CX bond and why does it takes place like that, right? So nature, or we can say the dipole of CX bonds vary according to the electronegativity of this particular halogen atom. So any kind of halogens are much more electronegative by nature due to its tendency to pull the electron towards it. So what is the electronegativity in this case? Electronegativity, suppose I am having a pair of electron in here and here, right? So this pair of electron will be shifted towards chlorine and it will pull the electrons from this position towards itself due to higher electronegativity. So this tendency of pulling the bond pair electrons, this is the bond pair electrons, right? Bond pair electron towards itself is known as the electronegativity, and due to this electronegativity we get a specific nature of CX bond. How it works? If the electron, the bond pair is pulled towards this one, the resultant will be, this one will be positive and this one will be much more negative. Why it is negative? Suppose in case of chlorine we are having 7 electrons in here in general, but when we are pulling a pair of electron towards us, so it's becoming a single pair would make it 8, a single electron will make it 8, and make a dual pair, a pair will make it 9, right? So in this case the total electron will be shifted to this side. The pair of electron when shifted to this side will make it much more negative in nature. Now while moving down the group, in case of halogen or group 7 and group 17, what we will see, we will observe that in case of chlorine, chlorine, bromine and iodine. I hope you can see iodine in here. Iodine, all of these will pull the electron pairs toward themselves to get a negative entity. So the resultant will be, this one will be negative by nature and this one will be positive by nature. And along the down the group, if we move down the group, the atomic radii are radii increases from fluorine to iodine, right? Then fluorine, bromine, iodine, this will be our series. So down the group, what would happen? The amount of energy, the amount of enthalpy or bond enthalpy, will be increased. Why? Let's see. As suppose this is fluorine, bromine, and this is iodine, right? Chlorine, chlorine, bromine and iodine is there. So in case of CH3F, the bond length will increase. The bond length will increase, right? As this one, suppose I am taking bromine in here, and this larger one is iodine, right? So what would happen in case of bromine? The CH3 will be in here, and in case of iodine, the CH3 will be in here. So which will have a much bigger bond length, which will decrease the bond enthalpy. Why? Because whenever we increase the bond length, what would happen? Suppose this is chlorine and this is CH3, right? What would happen if the bond length increases in case of iodine, CH3 and I? It will require more energy. Suppose this is E1 and this is E2, or del H2 and this is del H1. What would happen? Del H2 will always be much greater than del H1. Why? Because del H2 will be much less than del H1, as these two have they will have more attractive force between them, right? More force of attraction, and here this will be less force of attraction. Now more force of attraction and due to less force of attraction, the bond length in case of iodine will consume less amount of heat. To break this particular bond. So it will require much more amount of heat to break the bond, and it will require less amount of heat to break the bond. Hence, down the group from F, Cl, Br and I, we will have an increasing force of attraction. Number 2, we will get increase in bond length, increase force of attraction, increase in bond length, and decrease in bond enthalpy. The bond enthalpy will be much less. So del H down the group decreases. So this was all about down the group from F, Cl, Br and I. This will decrease down the group, right? So this is all about the nature of the CX bond. Let's move on to the next portion, that is the procedure or methods of producing a haloalkane.